Hello everyone, welcome to the post-contest discussion of the Codeforces Educational Round 170. I'm Abhinav and this is TLE Eliminators. So let's get started with the first problem. Okay, so the first problem was there are two screens. Okay, sorry, if anybody is doing that, please don't do the annotation thing. Okay. So in this problem, it's given that there are two screens which can display sequence of uppercase Latin letters. Initially, both screen display nothing. In 1 second, you can do one of the following two actions. Choose a screen and an uppercase Latin letter and append that letter to the end of the sequence displayed on that screen. And the second action is choose a screen and copy the sequence from it to the other screen, overwriting the sequence that were displayed on the other screen. So basically there are two screens and in every second you can do either of the two operations. Just choose a screen and add a uppercase letter to that screen, or choose a screen and copy the entire content of that screen to the other screen. Okay, these are the two types of operation you can do in 1 second. You have to calculate the minimum number of seconds you have to spend so that the first screen displays the sequence S and the second screen displays the sequence T. Okay, so you are just given two sequences. You have to make the first screen display the first sequence and the second screen display the second sequence. And you have to do that in minimum number of operations. And there are two types of operations. Okay, so what you can do here is, let's say you are given this test case. Okay, so you have two screens. What's given is you have two screens. Okay, initially both the screens are empty. Okay, so there is nothing displayed in both of the screen. Now in every second, what you can do is, let's say you selected the first screen and then you'll add any letter to that screen. Okay, so you have to make the first screen to have garage and the second screen to have garage for sale. Okay, so let's say you added a G in the first screen. Okay, to get this. Then this is in the first second. Next second, you can add a to the first screen, then R to the first screen. Okay, that way you can make this complete garage in 1, 2, 3, 4, 5, 6 seconds in the first screen. And then what you can do is start for the second screen, add a G, then a, then a R. Okay, that way you would do it in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, there are 13 letters in this and 6 letters in this. So one way is just do only the operations of first type and just add one letter. So in 6 seconds, you can do this. And then in 13 seconds, you can do this. Okay, this is one way. But you have a second type of operation also here, that what you can do is, if you have some characters on the first screen, you can copy the entire thing to the second screen. That is also allowed. So in this case, the best thing was just write these 6 letters in the first screen, garage, and then this garage was common for the second screen also. So what you could have done is, in 1 second only, copy this entire thing here. So what would have taken you 6 seconds to six type 1 operations to do this, you can do that in a single type 2 operation after you have written garage in the first screen. Okay, so here the best way was do it in 6 operations, then this whole thing in one operation, and then this much thing, there are 7 letters, so one by one, 7 operations here. So 6 + 1 + 7 would take you 14 operations. This was the minimum for the first test case. If you see, 14 was your answer. Okay, but what's the now? How would you decide how would you basically go around this problem to minimize your number of operations? Okay, so if you see, you have two types of operations. Okay, the operation one is just add a letter. Okay, you can add a letter only at the end. Okay, you cannot add at the start or anything. And operation two is just copy one screen to another. Okay, these two types of operation you have. Now if you use only operation one, then you can do this in the number of characters in S and then plus the number of characters in T. Okay, so S dot size plus T dot size. In this much operations, you can always do it. But if you want to minimize it, how would you do that? Is uh, if in one of the screen you have something and the same thing is required in another screen also, then you can use a type 2 operation to copy that entire thing there. But you have to make sure that in both the operations, you can only add some letters. You cannot delete any character from any screen. So if let's say in the second screen, instead of this A, you had some E. Okay, let's suppose instead of this A, you had some E. Then if you wrote the entire garage here and then copied that there, then you had a A. You cannot replace this with E. You cannot delete this entire thing. So in that case, you wouldn't use this entire thing there. What you would do is you would only use that much thing which is common to both of the words. Okay, both of the strings. Only the prefix that is common to both of the screens, both of the strings, that would only be used here if you analyze. Because if you use anything else, okay, if you try to, let's say there is some substring here which you want to copy to another screen. Now, whenever you want to make this word, you can only add letters at the end. Okay. So if you want to make this garage, and let's say you started with an A and then wrote an R, you use some substring in the middle, then you cannot add a character from the start. So always it's necessary that you move from the start to the end only. Okay, so whenever you want to make a complete word, you would have to move from the start to the end only. So you cannot select a substring from the middle. So you know that always you would have some prefix of the what you want to achieve. Okay, so in both your screens, they should contain only the prefix of what you want to achieve at any time. Okay, so if at any time both the screens should only contain the prefix of what you want to achieve, so what is the best thing you can do with a type 2 operation? Type 2 operation you can use when two of the strings have something in common. So what they can have in common is a prefix. Okay, if there's a prefix common with something in the middle, that you cannot utilize. You can only utilize anything, any prefix, any two common prefixes. They can be utilized to basically, if there are three letter prefix which is common, then instead of three operations, you can do it in one operation after doing this. Okay. So basically, find what you have to do finally is, if you would have used a type 1 operation, your answer would have been, let's say, uh, the size of S is N. Okay, I'm telling there are two strings given in my input, S and T. Okay, I'm telling the size of S is N and the size of the second string T is M. So using only type 1 operations, I can make it in N plus M seconds. And if I use type 2 operation in that, then what is the reduction I can do is, the reduction I can do is number of characters which are common from the beginning if you analyze. So if the two strings are starting from different character, let's say we have a ABC and a BBC, something like this. If both of them are starting from different characters, you just cannot use a type 2 operation anywhere, because in order to make the first string, you would have to start making it from the start. So if you add an A, which is not required at the start in the second string, then you cannot copy anything in this, because after that you cannot delete anything which is not required. So you can only copy a common prefix. Here there was nothing in common, so you cannot, it's not optimal to use a type 2 operation in this case. So if both the strings are starting differently, N plus M would be your answer. Now, if you had A in common, the first character is common, and let's say the second character is not common, then what's your answer? Three operations would be utilized here. Okay, so before using the three operations, what you could have done is use one operation here and then copy this A that side. After that, use a B and C. But again, copying this A is going to take you 1 second, and you could have replaced this A with A in 1 second anyways. Okay, so in this case only your answer would be like 3 for this and 3 for this only. So it would be n plus m only. Where you can improve is if you have two characters in common. Okay, ABC, and let's say this is. Okay, if you have something like this is your test case, then what you can do in first second, you do this A in the first screen. Okay, you have the two screens. First second, you add an A. Next second, you add a B. Then this AB was the maximum common prefix in both of them. So you copy this entire AB to that side in the third second. Fourth second, you add this D. Fifth second, you add this E. So instead of using 3 plus 3, 6 seconds, we did it in 5 seconds only. Okay. So if the max, so we would just calculate the maximum common prefix in both the strings. Okay. So just start iterating from the first character. If they are common, add a plus one. If they are same, add a plus one. Whenever you have a different character, just stop there. Okay. So you had a length of 2, which was common there. So you can do a minus one. Okay. So because instead of 2 seconds, you are now using only 1 seconds. So if you have a length in both in your first string and your second string, if x length is common, I'm telling that the maximum common prefix in both of them is of length x, then in from your original answer, instead of using x seconds, you are using only 1 second. So basically you are doing a reduction of x minus 1 second. Okay. So your final answer is basically n plus m minus x minus 1. Okay, this you can say is would be your final answer, where x is maximum common prefix, you can say. Okay, so apart from the first common prefix, every time you are increasing the length, you are reducing your answer by 1 from n plus m. Okay, I hope this is clear to you. Okay, if there's any doubt in the first problem, you can say. Otherwise, I hope most of you would have solved the first problem. It was very easy to understand this. So let's move to the code part of this. Okay, so what I did, I stored my initial answer as s dot size plus t dot size, which was my n plus m. Okay, this is my initial answer. Now, if my first character is only different, I just print this answer and return. Otherwise, I'll start with I equal to 1, go up till the minimum of both the size. Okay, because if I reach either the size of S or size of T, after that the indexing of one of the string would finish. So your maximum common prefix can't be more than that. So we are running the loop only till minimum of N or M. And then whenever you get a, until you are getting SI is equal to TI, we do an answer minus minus. And whenever this condition is not satisfied, the first time you get something unequal, we break out of the loop. Okay, so that way. So this x minus 1 thing that I wrote in my formula. Okay, so that I'm reducing one by one, starting with I equal to 1. Okay, until I get something in common, I'm reducing my answer. And if I get unequal, then I break out of the loop and print my answer. Okay, I hope this problem is clear to you. Okay, so if you just analyze the time complexity, I'm at max, I'm moving to the size of S or size of T. So its time complexity would be minimum of the size of S or size of T. And you can see in the problem, its constraints was very less, 100 only. So order of 100 is well accepted. Okay, let's move to the second problem now. Okay, in the second problem, what we are given is recently Akshim met a task that needed binomial coefficients to solve. He wrote a code. He usually does that look like this. Okay, so you know that if you want to write the code for calculating NCR, the binomial coefficient, okay, so the actual recursive formula to calculate this is this, that NCK is basically n minus 1 CK plus n minus 1 CK minus 1. Like if you know some maths, then this is the actual formula. If you want to compute NCR, then you compute using, if you are doing a DP approach to compute NCR, this is the actual formula to do this. But what this guy did is, instead of using this formula, he wrote this formula. So instead of C n minus 1K, He wrote C N K minus 1. Okay, so he just made a mistake in his code. Now, you have to assume that this mistake code is only the correct code, or for this code, basically, you have to then find NCK. Okay, so if this was the way of calculating NCK, then what would be your NCK modulo 1e9 plus 7? You have to just find out. You are given T pairs of N and K. Okay, so for every pair you have to answer. So basically you can assume there are T test cases. For every test case, you are given a N and a K, and you have to find NCK, assuming that you are using this wrong formula. Then what's the NCK? Modulo 1e9 plus 7 that you need to find for every test case. Okay, so if I try to look, okay, let's take this was the test case given to us. Okay, so here, okay, let's only take the first few test case, 255, 1, 2, 3. Okay, instead of taking all this. Okay, let's say this was the test case. So you are given T test cases here. In general, when you are given T test cases, you are given these two together, but the whole N array is given together and K array is given together. So don't you count it as T test cases, count it as, let's say, T queries. Okay. So you would take all the T n's together and the T k's together. Okay, the array of N and the array of K. Okay, so basically what you need to do is for every I. Okay, so if you start from, let's say, I equal to 1, 2, 3, if I'm doing a 1 based indexing. Okay, so let's say you are calculating for I equal to 1, then your N is 2 and K is 1. Okay. Okay, if you are calculating this, okay, so one by one you have to calculate for every N and K. So you have to answer, if your N is 2, K is 1, what is C of 2, 1 according to the formula written, or according to the code written by this person. Okay, so like what you could have done is just use this code only and compute it. But what its complexity would be, you can see it's running a loop of N into K. Okay, so you are running a loop of basically N square, or N into K times you are running. And if there are T test cases and N and K are up to 10 to the power 5, so overall time complexity would be basically, for T test cases, they are 10 to the power 5 test cases. And if you are doing N into K every time, 10 to the power 5 into 10 to the power 5 every time, that would exceed. Now, what you could do is you could just pre-compute up to 10 to the power 5. But the pre-computation would also take you 10 to the power 5 into 10 to the power 5. Okay. Order of N into K, if you are doing. So Ni into Ki. You can just pre-compute all the values up to 5,000 using this formula. But that would still take you N into 10 to the power 5 into 10 to the power 5, which is not going to get accepted. In 1 second, you can only do 10 to the power 8 operations. So you need to calculate this in some optimized way. How are you going to compute this C of Nk in some optimized way, not in order of N into K? So let's analyze what would happen if we are calculating like this. Okay. So you can see the code, what is happening for a particular N. We start with N equal to 0. Okay, we have N and K. Okay, so we are just doing this computation. Let's write it like this. Let's make a table, and there we will write. Okay, so this is N and this is K. So with 0, 1, 2, 3. Okay, this was how I thought this problem in the contest. I just tried to calculate, like whenever you write a DB, you get a table basically. So just try to do the table calculation according to the given formula. Okay, how this tabulation is going to work. This DP tabulation is going to work with the given formula. Just let's dry run this on some values so that we can find some pattern in this. Okay, so what you can see, for N equal to 0, we would start. For N equal to 0, n0 and n is 1. So 0, 0 and 0, 0 both are 1. So for n equal to 0, we get 1 here. Okay. We get a 1 here. So for n equal to 0, you are not going there. So these would just remain empty. For any n, you are only going k less than equal to n only. Okay. So you would have values only till here. This part would remain empty. You can understand that because this k is going only less than uh, only till n you are computing. Now for n equal to 1, 1, 0 and 1, 1, they both would be set to 1. So 1, 0 and 1, 1, they both would be set to 1. Now for n equal to 2, what would happen? 2, 0 and 2, 2, they would be set to 1. So 2, 0 and 2, 2. Okay. So these two values are set to 1. Now this 2, 1 is calculated inside the loop. Okay. For k equal to 1, k less than 2, you can see. So C of 2, 2, that is C of 2, k minus 1. Okay. Let's write this code there only. So okay, let's write just this recursive formula. Okay, this was the formula through which we are computing. Okay, and the base case was that C of n 0 is 1 and C of n is 1. Okay, so and then this was the formula through which the remaining values greater than 0 and less than n are being calculated. Okay, so for n equal to 2, the this value and this value were 1 through this base cases. Now the middle values are calculated through this formula. Okay, so for C22, what it would be? C2 k minus 1 is 1. C21, it is this value. And then, sorry, C21 is this value. Sorry, n is 2 and k is 1. Okay, so we are computing. Okay, we are computing C21. Okay, so C21 can be written as C2 0 plus C1 0. Okay, so according to this formula, C21 would be like this. So C21 is C2 0 and C1 0. Okay, so it's the sum of these two values. Okay, so this was sum of these two values, which was 2. Okay, now if we move to n equal to 3. Okay, so when we move to n equal to 3, we get C. Okay, the base case is C30 and C33. They would be 1. So C30 and C33, they would be 1. And then you would move like this. Basically, for the middle parts, C3 1, C31 would be C30 plus C20. Okay, so C31, this value is C30, which is this value, and C20, which is this value. Okay, the sum of these two values is this. Okay, so this was sum of these two values. Now, if you calculate the C32, if you wish to calculate C32, that would be C31 plus C21. Okay, so C32, this value is C31. C31 is this, and C21 is this. Okay, so it's the sum of these two values. Okay, so this is the sum of these two values, which is 4. Now you would have understood the pattern here. For 4, it is 1 and 1 there. Now this value would be the sum of these two values, which is 2. This value would be the sum of these two values, which is 4. This value would be the sum of these two values, which is 8. Now, if we move to 5, we would have a 1 here and a 1 here. This value would be the sum of these two values, which would again come 2. This would come 4. This would come 8. This would come 60. So basically, you can see that the values are powers of 2. Okay, just by doing this tabulation, a dry run of this tabulation, you can understand what pattern you are getting. So every time for any n, for k equal to 0, all the answers would be 1. For k equal to 1, it would be 2, except when they are equal. Okay, so the equal cases would be 1. Okay, and I think you are given that they are not equal. Ki is less than ni, so the equal case is not given here. So you can just ignore these equal cases. Then what you have for k equal to 0, it's 2 to the power 0. K equal to 1, it's 2. For 2, all are 4. For 3, all are 8. For 4, all are 14. Basically, your answer is 2 to the power k. That's what your answer is. N does not matter here. For any n you are given, the answer only depends on k. For k equal to 0, you only get 1. For k equal to 1, you only get 2. For 2, you only get 4. Okay, so 2 to the power k is your answer. That you have to just answer modulo m. Okay, modulo 1e9 plus 7. So basically, for every test case, you can just calculate 2 to the power k modulo 1e9 plus 7. So to do the modulo thing, you have to write your own binary exponentiation function where you are doing modulo m in every step. So I hope you got what you have to do. Okay, so you can look at the given test case. For like you can look here for the first test case where n was 2 and k was 1. So it doesn't depend on n. K is 1, 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. And then 2 to the power 4 is, okay, sorry, there was 2 to the power 1. 2 to the power 1 is 2. 2 to the power this much modulo m would be something like this. Okay, so I hope you got what the question was. So let's see the code. Okay, you only have, we took the input. Okay, we have to, we just took two vectors n and k. So for every, we took n of size t and k of size t. This rep is just a for loop from 0 to 2. Okay, this is a for loop from 0 to t. Okay, so this is just the input part where I just took the input. And after that, this is just my answer complete. For every test case, my answer is 2 to the power ki. So this power function is a binary exponentiation function which is here. So I hope you know how to do the binary exponentiation. Modulo m, I am just doing a modulo m every time, x mod m, and every time I'm doing a mod m. Okay. So 2 to the power x, basically any x to the power n modulo m, this is the general function for that. So I just wrote that function, 2 to the power ki. That's my answer for every test case. I hope this problem is clear to you. Okay, it's time complexity to calculate the binary exponentiation. Its time complexity is log n or log of this ki. So for every test case, I'm doing a log n thing. So my final time complexity, I hope you understand, is t into log k, you can say. Okay, this would be my final time complexity. Repeat that part, that value depends on k only. You can see this tabulation. For the given code, I just tried to compute some values for the given code. What is my C of nk? Okay, so this is my n, this is my k. So my C of 0, 0 was 1. For n equal to 1, it was 1, 1. For n equal to 2, 1, 1 here. And this 2 was sum of these two. Then for n equal to 3, according to the formula of 1, 1 here, then this was the sum of these two. 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 Okay, so likewise, we were calculating. So just by doing this dry run, I hope you got for any n k equal to 0, we always have 1. K equal to 1, we always have 2. Then for k equal to 2, we always have 4. Okay, so I hope you, just by looking at this, you can understand that it's not depending on n, it's only 2 to the power k. Yeah. Okay. So I hope the second problem is clear to everyone. If there is any other doubt in this, you can ask, or we'll move to the third problem. Okay, so let's move to the third problem. There's a new game Monocop wants to play. The game uses a deck of n cards where the ith card has exactly AI written on it. At the beginning of the game, on the first turn, Monocap can take any card from the deck. Using each subsequent turn, Monocap can take exactly one card that has either the same number or the on the card taken on the previous turn, or a number that is one greater than the card taken on the previous turn. Okay, so the same thing is written here. After Monocop takes a card on the current turn, it is removed from the deck. According to rules of the game, the number of distinct numbers written on the card that Monocop can take must not exceed k. If after a turn Monocap cannot take a card, the game ends. Your task is to determine the maximum number of cards that Monocap can take from the deck during the game, given that on the first turn he can take any card from the deck. Okay, so in short, if I tell you what the problem states is, you are given an array. Okay, so this is your n, this is your k, and this is an array of size n. This is what you are given in input. What you have to do is one by one, you have to pick some values AI from this array. Let's say you picked 2. Okay, so you would remove this 2 from here and you get this 2. Okay, so Monocap picks this 2. After that, the next value that you can pick from the array, from the remaining part, should be, if your last picked value was x, the next picked value can be x or x plus 1, not anything else. Okay, so either you continue with this 2 again or you make it 3. Okay, so you can select either 2 or 3. Okay, let's say you again selected a 2. So you would get a 2. After this, you can only select 2 or 3. Now you don't have a 2. You would have to select a 3. Let's say you selected this 3. Okay, after this, you can select either a 3 again or a 4. Okay, so let's say you selected a 4 after this. Okay, this way you have to move. Now you have to find the maximum number of values that you can select. Okay, just determine the maximum number of cards that Monocop can take from the deck. Given the constraint, this k, what does this mean is the total number of distinct numbers that comes on the those cards that you have taken that cannot exceed k. So here, if you take till 4, you can see there is 2, there is 3, there is 4. So there are 3 distinct values with you. So, but your k was 2. So this is not allowed. Okay, you can have a maximum of 2 distinct values only here. Here you had 3 distinct values. Okay, so taking this 4 was not allowed basically here. So after this 3, you cannot take a 4. So maybe you try to take another 3 until you can take it, or you cannot take a 2 again after taking a 3. Okay, so you just need to find the maximum number of cards you can take, keeping this constraint in mind and this x or x plus 1 constraint in mind. That way, the maximum number of cards you can take, uh, and you are given that you can start from any card. At the beginning, the first card that you take can be just any card. Like we selected 2 here. You could have begin with 3 also. Okay. So then you have to find the maximum number of cards you can take. I hope the problem statement is clear. Like for this test case, the best answer was if you start with, I think 3. Okay. If you would have started with 2, after 3, you cannot take any 4. So what would happen? After 3, you would have to take this another 3, then again a 3, and then you cannot take any more card. You, after 3, you can only take either 3 or 4. But if you take a 4, you would have 3 distinct cards, so you cannot take a 4. So you just don't have any way, and your game ends here. So in this way, you took 5 cards. Okay, but what if you started with 3? Okay, let's say you started with 3. You took this 3. After this, you can take another 3. You can take another 3. Then you can take a 4. Then you can take another 4. Then you can take another 4. After this, you can either take a 4 or a 5. But if you take a 5, you would have more than 2 distinct values. You already have 3 and 4, so you cannot take a 5. So after this, the game would end. And here you have 6 values. Okay, so the maximum you can take in this particular test case was 6 using this way. Okay, so for the first test case, you can see your answer was 6. I hope the problem statement is clear to you. Now, just by analyzing the problem statement, you would have understood this small thing, that what's the sequence that you are taking. If you started with 3, just take all the 3s and then move to 4. Because if by taking these 2 3s, you jumped to 4, you would miss taking this another 3. So until, if you have started with an x, just take all the x available until there is some x available, then only move to x plus 1. Okay, then you would move to x plus 1, then take all the available x plus 1, then only move to x plus 2, and till where you would move. If your starting point was, let's say S, then at max you can move to S plus K minus 1, you can say, because you can have only K distinct values. So if your starting point was 3, then 3 plus 2 minus 1 is 4. So at max you can move up till 4. Okay. If you go to 3 plus 2, which is 5, then you would not take it. So you have to just find a k consecutive, basically k consecutive values whose sum of frequencies, you can say, because what's the number of values that you took here? For 3 there were 3 values, for 4 there were 3 values, so it's the frequency of 3. So the first thing that you can do here is, okay, just by analyzing this, what came to your mind is, from this array just compute the frequency array. What does I mean by frequency array? Which would denote the frequency of every element. So here you can see this 2 is the smallest value. 2 is occurring one time and two time. 2 is occurring two time. 3 is occurring one, two, three times. So 3 is occurring three times. 4 is occurring one, two, three times. Okay. 5 is occurring one and two times. Okay. So you can see this is the frequency array, basically, you can say. Okay. So in a map, you can just store this, the frequency array of this given array. Okay. Just the frequency map of this given array can be stored. Now, once you have computed this, what you need to find is, here k was 2. So you can either take these two values. So your final answer would be 2 plus 3, 5. So as you can see, when I started with 2, I had got 5. If you start with 3, what would be your answer is 3 plus 3, which is 6. Okay. If you start with 4, your answer would be 3 plus 2, which is 5. Now, what if you had, let's say, instead of 5, instead of these two 5, you had 6 here, and both of these 5 were 6 instead of 5. You don't have any 5. So here your frequency of 5 was 0, your frequency of 6 was 2. Okay. If this was the test case, then what would happen? If you start with 4, then after taking 3 times 4, you can only jump to x or x plus 1. Okay. So after 4, you can only take a 4 or a 5, but you don't have a 5. So after this 3 fours, okay, let's say your k was 3 ohm also, still you cannot take this to 6. So if you have a gap in the middle, if you have some element whose frequency is 0, then basically you can consider it like there's a bridge there. So either you would have some values above it or some values up below it. You cannot combine between the bridge. Okay. So you can just divide this problem into consecutive values which have some frequency. Okay, so whenever you have some value which doesn't have this frequency, so basically you can divide this, you can have a bridge here basically. So you can divide this problem into, this is separate, this is separate. So either from this find the maximum consecutive k values, okay, the maximum sum of frequencies for k consecutive values from this, or find the maximum sum of frequencies for k consecutive values from this, take the maximum among both of them. Or if you have more bridges here, then there can be multiple. Okay, so just divide this into sub parts of consecutive values having some frequency. Whenever you have some value which doesn't have some frequency, just break there and consider the next values as a new question. Okay, for that again compute, for that again compute. So that way you can just divide this problem into multiple subparts, calculate your answer for every part, and then the maximum among them would be your final answer. I hope this intuition, this logic is clear to you. Now, how can you do this overall thing optimally? Is, okay, like if you look at the constraints of the problem, what was the constraints is n was up to 2 into 10 to the power 5. So you cannot run something n square here. Okay, you can go something like n log n at max. Okay, so from the constraints you can understand you cannot go n square. You can, but you can go something n log n. So some map and all can be used here. So first of all, just compute the frequency map for this. So in n log n time, you can just insert these values into a map. Just do a frequency of basically AI plus plus. That way you can compute this frequency map in n log n. Then what you do, start with the first value. Okay. You have to just move in, like k is 2. So you have to compute the sum of these two values and then sum of these two values. So you have to just like take a sliding window type of thing. Okay, so the sum of this much. And then when you move to 4, just subtract this sum, add this sum. That way you can move your window there. Okay. So when you, if after that you had a 5, so when you move to this 4, subtract this, add this. So this sliding window would be moved to this. Okay. So just do a sliding window kind of thing. Okay. And keep calculating for k consecutive values. And whenever you move to some value, okay, like after 4, when you move to 6, so when you compare that the last value in the map, these two values differ by more than 1, that means they are separated. So from that, you just do a fresh start. Okay. So just do a fresh start and again start computing. So that's what the basically that's how you would code this problem. So I'll show you the code, and from the code only I'll explain you what I'm doing. Okay. I explain the intuition of my code, but you would understand better from the code what I'm trying to say. Okay. So if you move to the code. Okay, so in the code, what I am doing, just under this is a for loop. Okay, I hope you understand. Okay, so I'm taking the input part, C in AI, this a vector of A, and this is a map of int comma int. Okay, so this F is a map which is which is the frequency map basically. So whenever I take this AI as input, I do F of AI plus plus. This way I would compute my frequency map. I hope you understand that. Whenever I move to if I move to 6, I'll do frequency initially. In an empty map, the frequencies are 0, the values are 0. So 6 was 0 here. When I do uh, like f of 6 plus plus, it would become 1. That way, when I do f of 2 plus plus, that would become 1. That way, all the whole frequencies would be computed like this. Okay, so I computed the frequency map. After that, now I'm in order to do this thing, what I told you, that I'll move in separately. Okay, so whenever I encounter a value which where there was some gap, then I'll do a new start. So what I'm doing is when I'm moving through the map, okay, so when I've used an ordered map, so I would have things in ascending order only. Okay, the keys would be arranged in ascending order. So I'm iterating through the map. So when I start with 2, okay, so the first value I would start with, I take a variable st, which is the start, in which I'll store my starting value for the current block of elements that I am computing. Okay, so initially when I move to 2, I'll store my start as 2. And in order to check whether if I'm moving to this, let's say 6, in order to check whether this 6 was consecutive with the previous value or not, I need to store this 4. So in a variable L, I am just storing the last value that I had encountered. Okay, so these two variables I'm maintaining, L and ST. ST is the starting value of basically the block that I am in, and L is the last value just to check whether I have to change my block or not. Initially, I have assigned all of them -1 because I am not in any block. I have to begin. So -1 just denotes they are not assigned any value. Okay. And then I also have two variables, count and mx. So count would just store for my current, basically for my current sliding window, what's the sum of frequencies that would be stored in count, and mx would store the maximum among all the counts. Okay. So initially they are 0. Now I'll move to this map, this frequency map, this P. So whenever I'm iterating like this in a map, the P dot first, FF is first here. Okay. So P dot first would store the key and P dot second would store the value of the map. Okay. So this is stored in first, this is stored in second. So I'll first check if my, basically I would have two cases. Either my current value is uh, consecutive with the last value or it's not consecutive. So that I'll check with L if my current P dot first is not equal to like if my last value was not equal to p dot first minus 1, that means I'm not consecutive, I'm moving to a new block. Okay, so p dot first minus 1, so if for this 6, 6 minus 1 was 5 and my last value was 4, so they were unequal. If they are unequal, that means I am starting with a new block. So whenever I'm starting with a new block, I would have I would store st as p dot first. So this is my starting point, and my count would be p dot second. So when I'm just starting with some value, let's say I'm starting with this. So I only have this value. So this 2 would be the, my count would begin with 2. Let's say before that I had 3 plus 3, 6. Now when I'm starting here, my count would be reset to 2. Okay. So I have reset my count to p dot second, the value of the map, and my starting as the key p dot first. That's what I would do whenever I move to a new block. Now, when I'm in an old block, okay, in the else case, then what I would do is when I'm in this, let's say I'm moving here. Okay. So when I start until I reach k values, if my k was 2, so if I start with 2, then I'll add this. When I go to 3, I'll add this. So until there, I'll just add. When I'm moving to 4, then I would have to subtract this 2 from here. Okay. So I'll check the value where I'm moving minus the starting index. If that, okay, so what's the range of the total values I'm having? Starting minus that plus 1. Okay, so if my p dot first minus start plus 1. Okay, so this is the range from start till current value. This is the number of values we have. If that is greater than k, okay, so if that was less than k, then we would just add. But if that is greater than k, then we would also have to subtract what value? This. If I'm moving to 4, 4 minus k, 2. So this frequency I have to subtract also. So that I am doing. So whenever this is greater than k, then from my count, I would subtract the frequency of p dot first minus 1 minus k. Okay, so if this was my p dot first minus k was 2. So this f of 2, f of 2 would give me this value I have to subtract. So f of p dot first minus k, I would subtract from my count, and then I'll add to my count the p dot second. Okay. This I'll add in both the cases. Addition thing, whenever I'm moving to 4, this 3 would be added anyway. So I'm not writing an else here. Okay. This addition would be done in both the cases. Okay. Subtraction would only be done when I'm exceeding k values. Okay. So then I'll subtract. And that way, once I've done these three, this count would store the current count. So I'll maximize it with mx. And in L, I would store the p dot first, so that next p, when I go for the next iteration, I would have the last value stored in my variable L. So I hope it is clear what I am doing here. Finally, I would print mx, which is the maximum among all the counts. Okay. I hope you understood why subtract and sliding window thing. If you still have a doubt, you can write. Please explain the else part. Okay, so I'll again explain you. What I'm doing here is, okay, let's just dry run on this test case only. Okay, so once I've computed my frequency thing, this is what I get. Okay, so first in my P, I would have 2 comma 2. Okay, the first time when I'm iterating through this loop. Okay, so I'm iterating to my F. So P would have 2 comma 2 initially. That time what I would have, so that's the starting value. Okay, so it would go to the if, because the last was minus 1. Okay, so p dot 2 is not equal to 2 minus 1 1. Okay, so I'm starting, so starting would be stored p dot first, count would be p dot second. So my starting, okay, so starting would be this starting point 2, and my count would be this 2. Okay, this is done. When I move to this next value, uh, what would happen? I would go to the else part, because my last value was 2 and this is equal to 3 minus 1, 2. So I'm in continuation. So I would not move to this part, but I would move to the else part. Okay. Now what I'll do in the else part is p dot first minus st plus 1 is greater than k. What I mean is, what I need to maintain is at max, I can have k consecutive values. So here I only had this in my basically in my range. When I move to this 3, I have this much in my range. Now I can have both the values here because k is 2. So I don't need to subtract anything. I would add 2 plus 3. Okay. So there I would add 2 plus 3 and make my count as 5. Okay. So when I move to 3 comma 3. Now when I move to 4 comma 3, what would happen? This condition which I've written is p dot first minus starting. So p dot first is 4. 4 minus starting value was 2 plus 1 with 4 minus 2 plus 1 is 3 here. So 3 is greater than k. Okay. So if I include this 3, I would have a range of 3 values. Okay. So p dot first is my current value minus starting plus 1 is going to give me the number of values in this range. So the number of values when it is exceeding k, that time I would have to subtract this. Okay. So to maintain my sliding window. Okay. So I have to keep a sliding window of only size up till k. So whenever I have a size greater than k, I would subtract this value. So what is this value? This is my current value minus k, the frequency of that. So what I would subtract? I would subtract the frequency of current value is p dot first minus k. Okay, so that is subtracted from my count. So from my 5, I would subtract this 2, make it 3, and then I have to add this 3 in every case. So this thing is done in both the part. I don't need to check plus p dot second. So this 3 is added and it became 6. So for this value, my count became 6. So I'll maximize it. Initially, my count was 5. Here I had got a count of 5. Here I got a count of 6. Okay, so that would be the maximum. When I move to 6, what would happen? This last was 4 and my current p dot first is 6. So I can see that this case won't be satisfied. L not equal to p dot first minus 1. I'll have a new starting value. That way I would move. I hope you understood. But if frequency of 2 is more than 4, like that case is already considered. I'm handling all the cases. So if you are saying that frequency of 2 is more than 4, if it had, let's say 10, okay. So this case is covered in the first sliding window when I'm moving to 3. Then this 10 plus 3 is already covered. That 13 is there. Now I'm trying to find if I can get anything more. So I'm just sliding, sliding, sliding. That way I'm sliding to all possible cases. And among all possible cases, I would take the maximum. Okay, so this mx is max of mx comma cnt. So in cnt, I would get all the possible cases. I don't know which is greater, which is smaller. So I'll just take all the possible cases of length k. I would slide through all possible cases of length k, and the maximum among them would be my final answer. So this mx would have the maximum among all the cases. I hope you understand it. Okay. Okay, so I hope this problem is clear to everyone. If I analyze its time complexity, this inserting into a map takes log n time. So this would take an overall of n log n time. Okay, n times I'm inserting in the map. And then I'm iterating through a map which is at max size of n. So this for loop is going to run at max n times. Inside the loop, what I'm doing is this is order of 1. This is order of 1. This calculating frequency, it would go log n time because uh, anything checking in a map is also log n in a normal map. Okay, and then other things are order of 1. So at max, this is going n times and log n times. So that would also be at max n log n. So I hope you understand that the final time complexity would be order of n log n only. Okay. And my say space complexity would be just using a map of size n. Okay, that would go. So space complexity would also be order of n. Okay, I hope this problem is clear to everyone. If the problem didn't have any constraint on number of distinct numbered cards. I didn't understand what you're telling. If the problem didn't have any constraints on the number of distinct number cards. If you can open your mic and tell it is given to be less than k. Okay. Okay, this k, the k constraint you're telling, if we didn't have that, then just take the sum of all the frequencies. You don't have to consider anything. So just take the sum of all the blocks. Basically, would that would become more easy. Basically, this extra condition is not there. Only do count plus equal to sum for any block. Okay, just remove this and it would be your case. Okay. Okay, I hope this problem is clear to everyone. Like if what you are trying to say, but bridge will still, yeah, bridge would still be there if you have to consider consecutive things. The K is only doing this. Okay, I got it. Like there were two things. One was the consecutive thing due to which the bridge thing was coming, this if else, and the another thing was the constraint of K due to which this if condition was coming. Okay, so two separate things were there. Okay, let's move to the D problem now, I think. Okay, in problem D, what we have is imagine a game where you play as a character that has two attributes, strength and intelligence, that are at 0 level initially. During the game, you acquire M attribute points that allow you to increase your attribute levels. 1 point will increase one of the attributes by 1 level, but sometimes you'll encounter so-called attribute checks. If your corresponding attribute is high enough, you'll pass, otherwise you'll fail. Spending some time, you finally prepared a list of which contain records of all points you got and all checks you have met. And now you are wondering what is maximum number of attribute checks you can pass in a single run if you'd spend points wisely. Note that you can't change the order of records. Okay, so what this problem states is, okay, let's understand. So basically, okay, just ignore this. What you are given is, basically there are two things. One is strength and another is intelligence. Okay, so you have two attributes. One is strength, another is intelligence. Okay, so initially both of them are 0. Now one by one you would like in your records you get some points. Okay, so uh you you I you get M attribute points in total. Now you can convert that point to either increase your strength or increase your intelligence. Any one thing you can convert that point into. Okay, so like in the input, 0 represents that you got an attribute point. Okay, so like in the input format, you can Ri is 0. That means you acquired an attribute point. And then Ri greater than 0, Ri less than 0, what they denote is a strength check. Okay, so what you got initially, you got an attribute point. So either you would increase your strength attribute by 1 or your intelligence attribute by 1. Let's suppose in the first case, you increased your strength attribute by 1. After that, you got a check. Okay, so whenever it's a non-zero, it means it's a check. Now, if this value is positive, then this is a intelligence check. If this value is negative, then this is a strength check. Okay, so if this value was 1, it means it's an intelligence check, whether your intelligence is greater than equal to 1 or not. That's what this check denotes. Now, here you can see your intelligence was 0, not greater than equal to 1. So you would say you failed this check. Now, again, you got an attribute point. Now, you can either take this attribute point into add that into your strength or your intelligence. Let's say you added that to your intelligence. Then you got, again, this is a positive, so it's an intelligence check, whether your intelligence is greater than equal to 2 or not. That's the check. Now your intelligence is only 1, so again you would fail this. Then again you got a attribute point. Let's say you added that to your strength. Then negative denotes that's a strength check. -3, minus just denotes that's a strength check. The absolute value is 3. So whether your strength is greater than 3 or not, that's the check. So here your strength was 2 only. Again, you failed. Then you got some attribute point. Let's say you added that to strength. Okay, something, something. So whenever you, let's say here your strength was 4, and you got a strength check of greater than equal to 4, then you would pass that. Okay. Like here you would have to add that one which you added to intelligence into strength, then you would have 4. Okay. I hope you understood the problem statement. What you need to do is you have three types of things. Either a point. So that point you can decide whether you want to add that to your strength. Okay. So whenever you get a point, you can add that to your strength or your intelligence. Now, you have to add these points optimally so that these checks that you get, sometimes it would be an intelligence check, sometimes it would be a strength check. You need to pass maximum number of checks. That's your target. So you have to assign these attribute points to either to strength or intelligence. You have to decide which one you would assign so that you maximize the number of checks that you pass. That's the problem. I hope the problem is clear to you. For this test case, the most optimal way was answer was 3. So the most optimal way for this test case was you assign the first one to, I think, intelligence, then 2, and then 3. Explanation is going. Each point in strength, so you'll fail to. Okay, so if you spend each point in strength, that was the best way for this test case. So first you would add a strength, make it initially they were 0, make your strength 1. Then this is an intelligence check which you would fail. Then add it to your strength. This is an intelligence check which you would fail. Add it to strength, make it 3. This is a strength check greater than equal to 3, which you have. So you would pass here. Add a strength, make it 4. Strength greater than equal to 4, you would pass here again. Then add this to your strength, make it 5. Strength greater than equal to 5, you would pass here again. So a total of 3 pass you get. 3 was the maximum you can earn. You can try some different combinations also of adding, sometimes maybe adding to intelligence or other things. So for this test case, 3 was the maximum. Now you need to compute basically how you would find this maximum. Okay. And if you look at the constraints, M is 5,000. N is 2 into 10 to the power 6. Here, N is the total number of, basically the total history, number of attributes plus number of checks. The combined, this is N. And M is the total number of attribute points that you get. So at max 5,000 attribute points you would get. So there would be exactly M zeros in this arrays. Okay, so exactly M times you would get attribute points at some stages. Remaining of them would be checks. Okay, so the total number of checks plus attributes, they can go up to 2 into 10 to the power 6, but number of attribute points would only go up to 5,000. So you can understand from this constraint, then we can apply something order of M square. With 5,000, M square would work, but with order of N, you can just go up till order of N. So the required time complexity, like from looking at the constant, you can understand either you can go to something N or something M square. Okay, so you have to do something in this order. Okay, I like a plus or either N or M square or a plus of them, not a product. Okay. Okay, so this we analyzed from the constraints. Now, how can we think what we can do? Like, like someone wrote here also that we can do something with DP. Like in this kind of problem, whenever you have two options, either add it to strength or intelligence, you have two types of options. And where you have two types of options for these attribute points. Okay, so for these M points, you have two options, either add it to intelligence or strength. So straight away, I think DP should come to your mind, that you can do some DP counting. And also given the constraint that M was only up till 5,000, you can do something M square. So I think you can do some M square DP here. This can come, this I think should come to your mind. That's the first thing. Now we can do, but still, how can we think? What can we do? This N is up to 2 to the power 2 into 10 to the power 6. And we have to, what we have to do? We have to maximize the number of checks that are going to get passed. Okay. So if you look, just analyze the input. Let's say there was some attribute point. and then some checks, then an attribute point, and then some checks, attribute point, some checks, attribute point, some checks. Okay, like some checks initially. Okay, that would be the kind of input that you would get. Okay, like any input can be broken down in this way. Some checks, then an attribute point, some checks, then an attribute point, some checks, then an attribute point. Okay, so these attribute points are only M. Okay, these attributes point are only 5,000 in number at max. But this overall array is like 2 into 10 to the power 6 at max. Okay, so you have to apply some DP on these points only. Okay, so that's the first thing. Now, but what would happen to these checks? So what you can do is basically just when you move to this point. Okay, so like what DP state would you take whenever you are at this point? Either you would take it or not take it. Okay, so if you are at this point and you have to, among them, like you have two option, either add it to strength or to intelligence. Okay, so when you are at some ith, let's say ith intelligence point, you would have up till there, what all things can you have? If you are at ith intelligence point, you can have some, among that I, some number of points would be added to strength, some number of points would be added to intelligence. Okay, and you know you can run an M square. So what you can do is take a DPI, like the two states of the DP is, you can take a total number of intelligence point that you have occurred and a something J with where J is the number of among this total, how many are converted to strength, either strength or intelligence. Just take any one state. So if you have moved till a total of like this much points, among them J points are converted to strength. So TOT minus J points are converted to intelligence. Okay, that can be just, that is already stored in the state. You cannot, you don't need to take a third state to take number of intelligence point that you can compute by TOT minus J. Okay, so in one state, in this way you can just fix that up till here we have this many strengths and this many intelligence point. When you know exactly how many strength and how many intelligence points you have, then for these checks you know how many checks you would pass and how many checks you would fail. Okay, so I think then if you take this as a state, the computing things, whether you would pass or fail in these checks, that can be computed somehow. Okay, so that's the first intuition. So what DP state I'm taking is, this is the DP state. What it denotes is until, like till moving to, like TOT at, okay, let's, instead of writing it TOT, let's write it T only. Okay, if I have moved to T points until moving to the Tth uh, attribute point, yeah. So you have total M attribute points in total. So till moving to the Tth attribute point, if we take J out of T as either one you can take. Here I had taken as intelligence. Okay, as intelligence. Then what's my answer? Then the maximum number of pass until the Tth point. Okay, so if I'm at this T, then for this much thing, okay, just ignore the remaining. I'm moving one by one. Okay, so my DP state of Tj is denoting that till here, if among these T points, J of the points are taken as a strength, then what is the maximum number of pass that I can get? What is the maximum number of basically I can pass among these test, maximum number of tests that I can pass? That is my DP state. Okay, I hope you got the DP state. Now the main problem is how can we write a transition for this, because writing the transition was a bit tricky because you also need to consider these middle things. Okay, and you need to consider these in some optimal way so that you don't exceed some thing of this time. You can have some log factors in between. Okay, that would be okay. But you don't have to go something into n into m type complexity or n square complexity. They won't be accepted. So you have to keep that in mind. So this DP state is T and J. They would go to up to M and M. So this is an M square DP state. So you have to calculate the transitions in some optimized way in order of 1 or log n, something like that. If you go some order of n or m, then your overall complexity would exceed, like it is already m square, it would exceed. So you have to calculate the transition in some optimized way. So how can we calculate the transition? Okay, so let's say like if these things were not there, only the attribute points were there. Okay, and you had to complete like uh it's a very like general DP question where you have some points. You have to divide it into like two parts, either take it into some strength part, some T part. Okay, that way you, if you take this DP state, then the transition that you write is, if you take it into strength. Okay, so this DP, what it would be. So you have two cases when you want to compute DPIJ. That would be either this Tth point. Okay, the Tth point that I am denoting. This Tth point, either that would be taken to strength or intelligence. Okay, so one by one. If I am taking this into intelligence, that means till this point, okay, always I'll write the state in terms of, if I'm writing the state for T, I'll write in terms of T minus 1. So till this point, if I had an intelligence here, so how many intelligence point we, so what's the DP state we had till this point is, if I want to have J intelligence still here and this Tth is taken as an intelligence, then for T minus 1, I should have J minus 1 intelligence point, and then 1 intelligence point is taken here. So I'll transition using this DP state. Okay, so I'll transition using this DP state if I take intelligence as the Jth, Tth attribute. And if I take what strength as the Tth attribute, then I'll transition using DP of T minus 1 J, because I need to have J intelligence points in T minus 1 only, because the Tth point is a strength. Okay. So I would use these DP states to transition, but what would this DP state, if I'm taking as intelligence point, what would this DP state denote? The maximum answer until here. Now, after this, I would have to add the number of pass I get here. If I add that, then I can just write my transition completely. So plus in both the cases. Okay. So whatever DP you are taking here, that DP is denoting your answer until here. If you add this part, the number of tests you are passing in this part, you can just write your final transition for this. Okay. Now, how can you compute this part optimally? Is now you know, like for both the two cases, you know that till here, how many strength you have, how many intelligence you have. Okay. If you are using DPT minus 1, J minus 1, this means you have J minus 1 intelligence, and this minus this is your number of strength. So you know exactly how many strength and how many intelligence you have. If you know exactly, then you can just, for this, you can write like, if you just go to one by one to every case, then you can just find whether you would pass or fail. Your answer is fixed. If your number of strength and number of intelligence is fixed, then your answer is fixed. Okay, so if you store all the checks from here and then you compute how many you would pass, that way you can do. But if you do it one by one for every, basically what time complexity that would go is, like this is already m square. Now for every state, if you are like for every state, if you are going one by one to this, in total you would go n times. Okay, so like you can understand m square is only the this dp states are m square dp states are there. Now for the transition, if you are going one by one to every value, that would add multiplied by n to your overall time complexity. That won't be accepted. So you need to compute this thing in some optimized way. Okay. So how can you do that is when you move to this j, okay, so you are moving in this way. So while computing your dp, okay, you are moving in this way. So when you have moved till here, after that, when you move to this j, so before moving in the middle, what all tests are coming, just store them in something. If you store these tests in something, and at this point, you know that if I was at this point using two cases, so for both the cases, you know exact number of strengths and transitions, strength and intelligence. So if you know the number of strengths, so you can just store the all the test in two parts, all the strength test. Okay, so you can store all this, let's say in a vector you store all the strength test in this part. Okay, so let's say your vector v1 denotes all the intelligence test, and v2 denotes all the strength test. Okay, so let's say in this you had something like -2, -3 and 1. These were in the middle. So -2 denotes a strength test, -3 a strength test. So in strength test, you would have 2 and 3, and an intelligence test of 1. So you would have 1. So that's what I'm storing. In V1, I'm storing all the intelligence test, what all intelligence test came in between. In V2, I'm storing all the strength test, what all came in between. Now, in this vector, if I have this vector in sorted form, then just through a binary search, I can find out how many of this test would pass. If let's say at this point, I had number of strength equal to 2 and number of intelligence equal to 3, then how many would I pass? If there is a one intelligence test of 1, so it is less than 3. So I would pass one intelligence test. And if I look at strength test, if my strength is 2, then I would pass this test, but not pass this test. So again, one strength test I would pass, one intelligence test I would pass. So if this vector is stored in some sorted order, then just by binary search, just you can just use an upper bound function to find how many values are less than 3, less than equal to 3, or how many values are less than equal to 2. That can be found using a binary search. So that you can find in log n time in if this vector is stored in a sorted form. So what you would do while moving in computing the DP, when you are at this state and you have moved to this state, so before moving, you will encounter these things. So just store these things in two separate vectors, strength test in another, this in another. When you have moved to this, just sort these vectors. In n log n time, you can sort this vector. So overall, the sum of the sorting, if you calculate, at max, it would go n log n only. Okay. So in n log n time, so if you just sort this vector once, just sort it once, then all the states that you would compute for this. So for a particular t, you would compute basically t states. J would vary from 0 to t. Okay. So for before calculating all the states only, just sort that vector. Okay. If you're sorting it in every state, that would go m into n into log n time. So sort it beforehand only. And then while computing any state, just use a binary search. So you are just using an extra log n time. So basically, overall sorting thing would take n log n, and a binary search here would take a log n extra. So in n log n plus m square log n, you would be able to do it. Okay. So I hope you understood a bit what I am trying to do is, okay, while computing a DP only, just maintain these two vectors. Okay, so how would you maintain? When I move to some attribute point, okay, from that you begin. Like when I'm starting, just keep these as empty. Okay, so when I encounter a value which is not an attribute point, so if it is a strength test, add it to the first vector, second vector. If it is an intelligence test, add it to the first vector. That way, just move. Whenever you encounter a strength test, these vectors would contain these values. So accordingly, use upper bound, lower bound, and the DP transitions and compute the DP transitions for this state. Then clear these vectors so that when you move forward, these are cleared. So for this part is not there. So after computing the transitions, clear this, make this both vectors empty. And then again, when you move, they would again be recomputed for this part. So when you are at this point, again, you would have the vectors computed. In that you can sort them, compute all the DP states using binary search, then clear the vectors. I hope you got what I would do in the code part. So I think I can move to the code. There only I'll explain better what I'm doing. Okay, so what's my like DP transition? If I want to write this plus this value is computing it using binary search on both the vectors. You can see, like, if you know the strength value here, my strength value is or my in this J is denoting intelligence. I is intelligence value is J minus 1. Strength value is T minus, like T minus 1 minus J minus 1, which is coming out to be T minus J. So I know the exact strength, intelligence and strength. So I would, if my intelligence is I, number of values less than I in my V1, that I would add number of pass, number of values less than I in V1, that I can compute using upper bound in V1. So whatever index that is pointing, difference from dot begin with give you the that value. So like you can write it as V1 dot upper bound I plus V2 dot upper bound. For V2, I would do upper bound S. Okay. So this thing would be the number of passes you would have. Okay. So that you would compute and add. Same way like for this also. Here your I and S values would change according to this only. And that way you would compute. Okay. I hope. And you would take the, among these two states, you would take the max. Okay. Max of this or this, whichever is maximum, that you would take as this DP state. I hope you understood the transition. This was the state, and my base case, what would be my base case is when I'm at 0, when I have not encountered anything. And if I have not encountered anything, I would have to keep the number of intelligence points also 0. That would be 0. Basically, I have not passed any test. This is my base case. These are my transitions. What would be my final answer? My final answer, again, for that you would have to compute for when you have moved to the final intelligence point. Okay, when you have moved to the final intelligence point. After that, also for the remaining values, you would have to do this upper bound computation once for all the J, like for all DP M J. So this J varying from 0 to M. So if you have total M points, you can, among this M, you can either have 0 intelligence or M intelligence. So for all the DPJM, for all these DP, add this value accordingly, and among them take the maximum. That would be your final answer. Okay, let's show you the code, then you will understand better. Okay. So what I'm doing here is I took the input first, N, M, and this R. Okay, input is done. Then my DP was M cross M is my DP. I hope you understand. If this T can go at max M, this J can go at max M. So I've taken an M cross M DP. My base case is this DP00 equal to 0. As I wrote, this is my base case. Then I'm maintaining two vectors, V1 and V2. V1 stores that in this current block, what all intelligence tests have occurred. V2 stores the strength test that have occurred in my current block. TOT is my T, basically my DP state. Okay. So like here, when I would be moving, I would be moving through this R array. So that index won't denote my DP state. My DP state would be the number of intelligence tests that I have occurred. So that I'm maintaining in a variable T. So T is TOT, total is initially 0. Okay. And then I'm moving to this whole input array R. If Ri is greater than 0, that means I encounter the intelligence test. I would push that in V1. If it is less than 0, then I would push that in V2. Since Ri was negative, I'd push minus Ri to make it positive. So I'll push these values in V1 and V2. And if I encountered Ri equal to 0 in the else case, that means I've encountered an intelligence point. I would sort these two vectors. Okay. So first I would, what I told you before computing the states, I would sort these V1 and V2 so that I can apply binary search in that. I'll do tot plus plus because I have encountered a point. So I'll do tot plus plus. Now for this, I would compute dp of tot comma j. J would vary from 0 to tot. Okay. So now I have to compute dp of tj. So I'll write these two cases. Okay. The two cases that I have, if I take the tth point as intelligence. Now, what I would have to check if like if this j is 0, if this j is 0, that means I am not taking any intelligence point among this t, then I cannot take this tth point as intelligence. So this case would only happen for j greater than 0. So that I have to make sure, otherwise this would become negative. And this strength would only happen for j less than t. If I have all the t as intelligence, then I won't have a strength. Okay. So for this case, I have to maintain j greater than 0 check. For this case, j less than t check has to be maintained. So for this case, if j is not equal to 0 or greater than 0, anything you can write, I would do the first case. For first case, C1 is number of intelligence points, which is j minus 1. Okay, so there are j minus 1 intelligence points and number of strength points is t minus j. So C2 is number of strength points, which is t minus j. So I have C1 and C2. I would apply upper bound V1 comma C1. Okay. So in V1, I would apply upper bound using C1 minus V1 dot begin. This would give me the number of values less than C1 in V1. And this thing is going to give me number of values less than C2 in V2. I hope you understand. The sum of this is the value that I'm going to add in my transition. So my dp is max of what dp I have, or dp tot minus 1 j minus 1 plus val. Okay, this transition t minus 1 j minus 1 plus val. Okay, this transition I've written. Same for this case, everything is almost the same. Only the C1 and C2 is going to change. C1 would be j here, C2 would be tot minus j minus 1 here. Okay, C1, C2 is changing. This formula for val remains the same. And this dp state would be tot minus 1 j plus val. Okay, t minus 1 j plus val. Okay, so I have computed both the cases. I have taken the maximum. So my transition is done here. After that, I'll clear my both the vectors so that when I move to the next checkpoint, it would store only the values in between the two checkpoints, not the earlier values are cleared up. Okay. So I hope this transition is clear to you. Sorry. After that, just to compute the final answer, I'll just repeat this procedure one time. So compute the final. I'll sort both V1 and V2. Now, like you can see, my DP state, if this is the mth checkpoint, my DP state is computed till here. Now, for these values are ignored in that. So that also I have to consider once to calculate my final answer. Now, for that, I would state this as like among these m values, I would either have zero number of intelligence point or one or two or up to m. So I'll use DP of mj, where j would vary from 0 to m. So j would vary from 0 to m, and I'll use DP of mj here plus mj plus val. This val is computed in the same way as before. C1 here is j, C2 is m minus j, and this val is computed. So my answer is maximum among answer comma DP mj plus val. So I hope this part is clear. I'll print the final answer. That's the whole solution. Is there any doubt in this? Okay, so what would be my time complexity here? If I look, this is input part order of n, m square dp. here, this loop is running n times. Inside that, I have some for Ri greater than 0, less than 0, it's an order of one thing. Okay. In this part, so this else part is running at max m times. I know there are at max m checkpoints. So this part is running at max m times. Okay. This you can say this is running m times. This sorting is done. So these vectors would contain at max the sum of the number of times it is sorted, it is n. So overall this sorting, the overall time complexity of this sorting is n log n only, not more than that, because the values they are containing, like they are cleared in every step, so they are sorted only one time. So I hope you understand, you are going n times, and so these values, any value sorted only one time. So n log n would be the overall time complexity for this sort function for all the uh, m times. Okay. Then this loop is running TOT times, where TOT is at max m. So you can assume in m times, this is another m loop. Okay. So m square. This whole thing is running in total m square times. Inside that, I'm using a log n complexity upper bound. Okay. So this is running log n times. So this is going m times. This complexity is log n. Okay, log n, or yeah, log n. So overall, it's m into log n. Okay, that's the time complexity for this whole part. So you can understand it's order of m square log n is the complexity for this upper bounds. And for this sort function, the complexity is n log n. Sort function complexity is n log n. So overall, this is the time complexity for this whole loop. Then this sorting is n log n at max. This computation is also m into log n. Okay, this is at max m into log n, which is less only. So I hope you understand the final type complexity that I would get is order of m into m into, okay, this is m square log n plus n log n. Okay, so this would be my final time complexity. This is well accepted for m. 5,000 into 5,000 is 25 E6 2E7 and into log n. This is almost up till 1E8 only, and n log n is also fine. Okay, I hope this problem is clear to you, so that we can move to the next problem now. Okay, let's move to problem E. Okay, like for problem E, okay, let's discuss this. Uh, in the most popular card game in Berlin, a deck n cross m card is used where each card has two parameters, suit and rank. Suits in the card are numbered from 1 to n and ranks are numbered from 1 to m. There is exactly one card in the deck for each combination of suit and rank. A card with suit A and rank B can beat a card with suit C and rank D in one of the two cases. This where A is 1 and C is not 1. Basically, a card of suit 1 can beat any card of like any other suit. And A equal to C, B greater than D, it means a card can beat any other card of the same suit but of lower rank. Okay, so this all these things is given, and then before the game start, they receive exactly half of his deck. First player wins if every card of the second player, he can choose his card that can beat it. Okay, so I'll explain you the problem statement. What it's saying is you are given two variables n and m. You are given two variables n and m where m is even and n can be anything. Okay. And their constraint is up to 500 only. Now, what the problem states is that you have a deck of n into m cards. Okay. So where there are n suits and m like ranks. Okay. M ranks. Okay. So basically, like you can assume if like in a deck of 52 cards, a normal deck that you know, there are 4 suits and 13 ranks, you know, like, so that you can assume like there is n suits and m ranks. Okay, so that's making a deck of n into m cards. Okay, so this makes a deck of 52 cards, like in general, if you know. So from that you can understand what it says is now what's the, like, who can beat another card? For that it is given that any card of suit number one. Okay, so the suits are numbered from 1 to n. Okay, the suits are numbered like this, and the ranks are numbered from 1 up till m. Okay, this way the ranks are numbered. Now any card of suit 1 can beat any card of any other suit. Okay, so if you have two cards of different suits, one of the card is belonging to suit 1, then the card belonging to suit 1 would win. Now for any two cards in the same suit, okay, so if there are two cards in the same suit and they have different ranks, the card having higher rank would win. That's the second case. Okay, so these are the two conditions given for any two cards who is going to win. If they are from different suits, then the card belonging to suit number 1 is going to win. Now if you have two cards from two suits which both of them are not one, then you cannot decide which one is going to win. Okay, so that is not given here. Only when you have a card from suit number 1, it will beat any card in any other suit. And for two cards in the same suit, we would consider their ranks. The one having higher rank would win. Okay, this is the cases given that which card can beat another card. Now you have to find out that there are two players, like player number 1 and player number 2. The first player and second player, that's all. So there is player number 1 and player number 2. So among these n into m cards, they would be divided half half to both the players. So player 1 would receive n into m by 2 cards. Player 2 would receive n into m by 2 cards. And you have to find the number of ways to distribute these cards such that if he has some cards, he has some cards, then this player 1 has a corresponding card to beat every corresponding card of player 2. Like, let's say player 1 has some 6 cards. Okay, let's say I'm telling the cards are 1, 2. Okay, every card would have a rank and suit. Let's say like 1, 1 and 1, 2, or 2, 1 and 2, 2, anything. Let's say there are 4 cards A, B, C, B. Okay, every card would have some rank number and some suit number. Okay, and this is belonging to player A, first player, and the second player has some cards E, F, G, H, which is belonging to the second player. Okay, if they have 4 cards, okay, then uh, it's a valid distribution if the player 1 can have a corresponding card to beat every card of player 2. So to beat a card of player, so basically you can just have a matching for every card. So if you can create a matching that card A matches to F, B matches to E, this way, let's say you create some matching so that in every matching the card of player A wins, the player 1 wins. Basically, for every card of player 2, he has a card to encounter it. Now, if this E can be defeated, like if this B can defeat two of the cards, E and F, then he can use it to defeat only one of the cards. So for F, he should have some another card which can defeat it. Okay. So I hope you understood the problem that for every card of player 2, there is one card with player A that can beat it. So you can create a matching like this so that the player 1 can beat every card of player 2. If you can find that is a valid combination. Now you need to find number of ways in which number of combinations you can create so that this happens. That's the problem. Okay, so let's see how we can solve this. Now, if you see the constraints of the problem, n are up till 500. Like if you look at 500, what complexities you can understand? 500 into 500, that would be accepted for sure. But something like a 500 cube, that is going like 1.25 into 10 to the power 8. So that would also be almost accepted. Okay. If you are doing it in some optimized way, if you look at the constraint of 500, okay, maybe some 500 cube by 2. that would be well accepted. Okay, or by 4, something like that. If you are doing it in an optimized way, this complexity would also be accepted. Okay, and square complexity is anyways accepted. So what you can do here is, okay, for any like this combination type of question, so let's move, like this was a little bit complicated to implement and all, also the logic was a little complex. So I'll tell you the logic in short only, not, I won't go in too deep. So what we have to do here is basically for like you can see, there are two ways to win. That if the player 1 has a card from suit number 1, he can beat any other card from player 2. Okay, so first thing, if player 1 has half of the card and player 2 has half of the card, for a valid matching, what conditions should be satisfied? So let's analyze suit number 1. How would you distribute suit number 1? So with suit number 1, there are M cards. And you know M is even. That is also given in the problem. Okay. Now, if let's say among these M cards, the card with suit 1 and value rank M, that's the card which is going to beat any other card. You know, like for any card of suit 1, it can beat any other suit. And for the same suit, if it has a rank of M, the highest rank, then this card 1M is going to beat, is like an unbeatable card. So you know for sure, if player 2 gets this card, that means this won't be a valid combination. Player 1 cannot defeat him. So this card should remain with player 1, that is for sure. I hope this conclusion you can draw, that this unbeatable card should remain with player 1. If it goes to player 2, game over. So for creating a valid combination, this should remain with player 1. Now, what more things should happen? Like if you just look at the first, basically the first suit, then from the first suit, if let's say player 2 has some X number of cards from the first suit, okay. So player 2 has X number of cards of suit 1, then I need to make sure that all the cards are defeated. So to defeat these X cards, if you have any card from any other suit, you cannot defeat a card of suit 1. So to defeat a card of suit 1, you need to have a card of suit 1. So if player 2 has more cards of suit, so every card of every card would be defeated by one of the card by player 1. So if how should the suit 1 be distributed? If let's say in suit 1, if the M is, let's say 6. Okay, so in suit 1, there are 6 cards. So you know this highest card should belong to player 1, that I concluded from here. But still, what if let's say all the remaining 5 cards belong to player 2? Then can the player 1 win? Because through this card he can defeat any one card, but then 4 card would be remaining, that would become undefeatable by any other suit. So you know for suit 1, there should be at least half of the card, at least half of the cards of suit 1 should be with player 1. I hope you can conclude that. If you have more than half of the card with player 2, then you cannot defeat all of those, cancel out all of those cards using the remaining cards, because only suit 1 can cancel. So you know from suit 1, at least M by 2 cards from suit 1 should belong to player 1. So greater than equal to M by 2 cards. Okay, so what if exactly M by 2 cards are distributed to player 1? Okay, so first, which all cards should be distributed, that you would have to compute. So you know this highest one is going to be given to player 1. Then if you move to this, like if this is given to player 2, let's suppose, and then this is also given to player 2, then this can defeat any one of the card. Now to defeat this, if he has, player 1 has a lower value card, he cannot defeat this. So from the highest, I would have to move, and while moving in any step, if I have the total number of cards with player 2 greater than player 1, then I can say that it cannot happen. So while moving, I need to assign every card to either player 1 or player 2. making sure that player 1 always has greater than equal to the number of cards from player 2. So this thing I can do using a DP. I hope you can understand that using a DP state, I can maintain that uh, a 2D DP of M cross M. I can maintain that if I have to distribute M by 2 cards, then how many ways are there? Okay, that I can compute. So my final answer would be among, so I'll take a DP state of IJ, which would have that from beginning, like from the highest, if you are moving among the highest I cards, if I give uh, J of the cards to player 1, then what's my answer? And this J should always remain greater than equal to I by 2. Okay, the seal of I by 2. Okay, so maintaining that, if you maintain a DP, this you can write the transition, and from this, the DP M comma M by 2, this would be the number of ways if you have exactly M by 2 cards with player 1. Or if you have M by 2 plus 1 cards with player 1, DP M by 2 plus 1 would have that answer. So that way I can have, or I can give all the M cards to player 1 from suit 1. So these can be the only cases that either I would go M by 2 cards or M cards like greater than equal to M by 2 up till M. These are the number of cards that, these are the cases basically that I can have, that I can give to player number 1. Now let's analyze each case one by one. If player 1 receives exactly M by 2 cards from suit 1, I'm only analyzing suit 1 here. Okay. If player 1 has exactly M by 2 cards from suit 1, then for the remaining suits, how many, like, what should happen for this case for the remaining suits? Okay, so like in suit 1, M by 2 cards are with player 1, M by 2 cards are with player 2. So in suit 1, this is suit 1, this is suit 2, this is suit 3. Okay, let's say up till suit N. So in suit 1, I know there are M by 2 cards with player 1, M by 2 cards with player 2. So they would cancel each other out. The M by 2 cards of player 1 would defeat M by 2 cards of player 2. Okay, that I have to just make sure that they can cancel each other out. That I would make sure using the DP. Now from the second suit, I know for every card of player 1, I need a card of player 2 to defeat him. Now for other suits, if you don't have anything from suit 1, only a card from the same suit can defeat it. If you have a card of suit 2 and a suit 3, there you don't know what's the result would be, but you have to make sure that you are defeating it. So you would have to have a card from the same suit. So for every card of suit, any suit of suit I that player 2 has, there should be a corresponding card with player 1 which is going to defeat that. So basically for every suit you will need to have half distribution. Okay, exactly half of distribution if you are taking half distribution for suit 1, because anywhere if you have more cards with player 2, that won't get cancelled out with the cards of player 1. So for every suit I would have M by 2 cards with player 2, M by 2 cards with player 1, and the number of ways would be the same as computed using the above DP. So for this case I can say everywhere I would have the number of ways here was this thing. Here also the number of ways would be this. Here also the number of ways would be this. So for, if I'm assigning M by 2 cards, okay. So basically I have divided the question into cases. The number of cards from suit 1 given to player 1. Okay. So this can be either M by 2, or it would be M by 2 plus 1, or up till M by 2 plus I can say that can go up till M. Okay. These are the cases. So I can divide this entire question into this many cases, that from suit 1, if I'm picking exactly M by 2 cards, or M by 2 plus 1 cards, or up till M by 2 plus I, or at max M, all the M cards are with player 1. Now for this case, what's the number of ways that I know? If exactly M by 2 cards are given to player 1 from suit 1, then for all the decks, it should be half of half. So this DP. So basically for this, my answer would be dp of m by 2. This would occur how many times? N times. So this raised to the power n. This would be my answer for this test case. I hope you understand. This many ways for every suit, and there are n suits. So this would be the number of ways for exactly m by 2 cards. Now the problem gets trickier when we have more number of cards from suit 1. Okay. This was still a bit easy to find out. Now, when we have more cards from suit 1, sorry. So when we have more cards from suit 1, the problem gets even more trickier. Then what we would have to do is, let's say you have m by 2 plus 1 cards from suit 1. That means if you have more cards from suit 1, let's say there are m is 10. Okay. So let's say from suit 1, like player 1 gets 6 cards, player 2 gets 4 cards. Then these 4 cards would be cancelled out by the 4 cards of player 1, and we would still have 2 cards of player 1 from suit 1 remaining. So they can be utilized to cancel any other card from other suits, because a card from suit 1 can defeat any card. So basically from the other suits, any one of the suit can have like 6 cards with player 2 and 4 cards with player 1, so that 2 of the cards gets cancelled out by the 2 cards of player 1. Okay, so these extra cards that you can have for any other suit. So for m by 2 plus 1, you can, in any one of the suit, you can have an extra card with player 2. For m by 2 plus 2, you would have 2 extra cards, either either one extra in one suit and one extra in another suit, or 2 extra in any one suit. Okay. With I extra cards, m by 2 plus I cards from suit 1, you would have I extra cards in total among the other suits. So to write that state up, I'm using another DP to calculate that. That for this case, when I have m by 2 plus I cards from suit 1 belonging to player 1, then what's my answer? Okay, so this thing I am calculating using a DP. So for this, what I would do is, again, while calculating this DP only, one more thing you would have to do is, um, if you have m by 2 plus I cards, the number of ways to assign m by 2 plus I cards from suit 1 to player 1, that is going to be DP of m and m by 2 plus I straight away. The initial DP that we calculated, from that if we assign m by 2 plus I cards, that would be fine. But for the remaining states, I would move one by one. I would move in this way, one by one. And I'll say that I have to assign I extra cards. So first of all, I would have to compute if I'm assigning an extra card to with player 2, then what is the number of ways? So for that, I would pre-compute another DP, which I'm calling, let's say, DP1. Okay. That is, let's say, a 3D DP with a constraint of I, that there are I extra cards that can be assigned to a state. Then with I extra cards that can be assigned to a state, that means like if M is 10 and I can assign 2 extra cards to a state, like I equal to 1 means 1 extra card to a state. So I need to have a 6-4 distribution. So with that, with this initial DP, for computing this, the first DP that I told, the condition I was keeping is, okay, for this DPIJ, the condition I was keeping is that J should be always greater than equal to this. J should be greater than equal to CL of I by 2. Now, when I have a constraint that I can have I extra cards, then one of the cards from the top can be replaced to by some card from suit 1. So this condition is only going to change into J is greater than equal to I by 2 CL plus like the extra cards. Okay, this is I here, but let's say I can have X extra cards. If I can have X extra cards, just uh, minus x I can do. Okay, minus x. Okay, so j should be just I can reduce this range where j can lie. Okay, minus, if even I can do a minus x if there's one extra card, then if this j is half of the number of cards, total number of cards minus one, that would also be fine because one of the cards would be encountered by this extra card. So for x extra card, I can do a minus x in the condition, and then this dp that I calculated, this was for x equal to 0. So this was for x equal to 0. Now compute this dp for all x from 0 to m by 1, m by 2. So by changing the conditions. So okay, so that I'm calling it as dp1 of x, and the second state among this I only need the states of I as m and then j. So that with j is just the basically dp ij with condition of x. Okay, so dp ij with condition of x, sorry, dp mj. Okay, only for m. We'll compute ij and then only the states of m we will keep in the dp1. Okay, so this way I'm computing dp1, which is denoting if I have x extra cards and I need to keep a total of j cards in this, and I have a condition of x extra cards. Okay, then what is my value? So I would use this dp to compute another dp which would store. Okay, so this dp2 I'm telling is when I'm moving here, then for every basically if I move till here, I can have like the I here I'm telling is this. I can have in total I extra cards. So for every state, I can have either 0 to I. I would, so for this state, up this would have a DP of n, comma. So this would be for the rows, basically for the suits. Okay, for the n suits, if I move to the nth suit, there would be total n minus 1 remaining suits. So for those suits, if I have moved to the ith suit, then in that, if I have taken let's say j extra cards. Okay, so if I have taken j extra cards, then what is my number of ways? Okay, so this extra thing would be computed using dp1. So among j, the transition would be written like this: among this j, from 0 to j can be assigned to the current ith value, and from the I minus 1th value. So in order of m, I can write this transition. So this dp would be basically n into m overall. Okay, I'll show that in my code only. I know it is getting a little bit more complex, but this problem was a little complex. There are in total 3 dp used in this. Okay, so if you can compute like this for every case, then till here the sum of all those, okay, this multiplied by the thing that I computed there, sum of all those would give me the final answer. Okay, I'll show you in my code only now. Okay, so what I'm doing for that, you also had to do a little memory optimization thing, which I was not able to do, and I got a wrong answer. And then I upsolved it just after the contest, just after doing the memory optimization, it got accepted. So I missed the memory optimization there, and just before, and wasn't able to solve during the contest. So basically you can see that if you are using a 500 cube DP, it's like almost exceeding the 512 MB. So you have to use the memory optimized DP here. So what I would do is I'm taking the input n and m. Then first this DP2 that I am writing here is the DP that if I have X extra, like a condition that I can have X extra cards. The first state is the X extra cards. Okay, the I extra cards. I is the variable used for that here. If I have I extra cards, then among that, if I'm taking some J basically cards for player 2, then what's my answer? So that DP2 is computing using this DP. This DP is the initial DP that m cross m dp, that if I have m cards in my current deck, or in my current what you say, suit, that in any suit of m cards, if I have to select among the m cards, if I have to select I cards for a person, then keeping the condition of x, keeping the condition of I. So keeping the condition of I calculated this dp using this as the transition. Okay, so this was a transition. These are some base cases. You can read the code and understand. I hope this was the basically the transition. dpjk was j minus 1k or j minus 1 j minus 1 k minus 1 if you are not taking that, and j minus 1 k, like if you are taking that, it's j minus 1 k minus 1. If you are not taking that, then j minus 1 k. This was the dp transition overall for this, and the condition you here use was case would be less than ceil of j by 2 minus I. Okay, so if it is not the case, then dp is taken as 0. Otherwise this transition is used. Okay, so this minus I condition was used. If it was 0, that was the normal case for the initial, the very first basic TP that I showed you. But I converted that with a condition of I, that I can have I extra things also. I extra cancellations also I can have. Then only this condition is changed, then my different DP would be computed. So for every I, this DP2 would store whenever I move j equal to m, DP2 of ik as DP of mk. Okay, this DP2 I was not taking, I was using a 3D DP. So that was giving me MLE. So I optimized it using a 2D DP. Now this DP1 would store my answer, that uh, from if I'm at the nth, basically n is the number of suits. So if I'm at the ith suit, this time I'm moving in suit wise. If I'm at the ith suit and I have used some j extra, basically j extra cards that I can have, then what's the number of ways? So for that, my transition is dp1 of ij, like dp1 of ij is dp1 of ij plus dp1 of I minus 1 j minus k. So I'm running a loop that for this current suit, if I'm using k extra, okay, if I'm using k extra, then a total of j extra was there. Out of that, k extra are used in the current suit. So k can be from 0 to j. So if k extra are used from the current suit, then dpij would be from I minus 1, I have to use j minus k extra. So till I minus 1, if I use j minus k extra and k extra in the current. So if I am using k extra in the current, then for the current, I would use the condition of k with dp2 and this value of m by 2 minus k. Okay, I'm just using m by 2 minus k only cards because k extra are coming from there. So this was my transition for this. After that, once I've computed this dp1, using the dp1, I can compute my final answer for all the different cases. So for exactly m by 2, so this I is the extra m by 2 plus I. Okay, so this final case, when I is 0, for exact m by 2, dp m and m by 2. So this is dp2 0 and m by 2 plus I. So 0 is the condition of 0 extra. Okay, so for the first deck, or the for the like for suit number 1, I would always have the condition of 0 extra. For other suits, I would have condition of I extra. So for the, this is for the first suit, condition of 0 extra and m by 2 plus I cards from there. For the remaining suit, I have for the n minus 1 remaining suits, I can take I extra cards. So this TP1, that if I take, if I've already taken I extra cards in the first suit, then with I less cards, what's the number of ways? So this multiplied mod m is my x. I'll add that to my answer for every case. And I print my final answer. I hope you would have understood this problem. Otherwise, no problem. If I analyze the time complexity of this is m by 2 into m into m. These are order of 1. So this overall is order of m by 2 into m into m. So it's m cubed by 3. Okay. And this is n into m by 2 into this GUI is going up till M. So this overall is order of n into m by 2 into m. So it's m square by 2. Okay, this is overall for this loop. And for this is m by 2, just order of m by 2. So overall, if you see the time complexity, it would be m cube by 3 or n into m square by n cube by 2, it would be m by 2 into m cube by 3 or n into m square by 2. So order of n into m square by 2 or m cube by 2. So overall, if you see n and m are up till 500, so this is 500 cube by 2. This is also 500 cube by 2. So this is overall order of 500 cube, which is approx 1.25 E8. Okay. So for this, the time limit was given as 2 seconds. So 2E8 about is accepted. If you write it in very optimized form, it is accepted. Only you have to keep in mind the space complexity, that if for this, the space complexity is initially I was doing with n cube space, that was giving me MLE. But in this case, you can see this is a m into MDP, m square. This is n into m, and this is n into m. So overall, it's order of either n into m plus m square, anyone. Okay. So this square complexity of space is accepted. So you have to keep the time and both space complexity in mind in this case. I hope this problem is clear. So thank you very much for tuning in. Goodbye.